that's a quick demonstration of some cool music stuff. Sampling. Oh, here's a filter. All right. How's everyone doing? Today we will be discussing about the Z transform, and hopefully helping you understand what's going on. So I'll try to make this video pretty short. Well, not too short, but just to get a basic understanding of what's going on. So Z transform. It's an amazing tool. It's basically you know how the Laplace transform is used for analyzing analog systems. Well, the Z transform is for discrete systems, but there's a special little rule. So I'll just establish that right now. We're just going to go over how to practically do this. So the Z transform of a signal. The rule is we're going to analyze a signal from the first point, which is minus infinity, to the final point on that signal, to infinity, the entire signal of z to the minus n. And yeah, we just multiply that z to the minus n term. So that's how we turn it into the Z transform. So now the one thing I want to discuss is basically, well, what do we do? And what's a Z transform? How do we start with this Z transform? So let's say I wanted to choose, well, some finite signal. We're just going to use an example. Let's do this. And let's assume that a signal exists just for a few seconds. Let's just do this, 2, 3, just some random signal, whatever. Where the amplitude, let's just call it a of n. So it just changes as a function of, n. Is equal to 0, 1, 2, 3, and then let's just say at 4 it just turns off. It doesn't exist. So just do that for an example. So what we're going to do is, well, we have this signal that we can, let's just define it as, it has an amplitude of an. It exists at u of n, so it starts at n is equal to 0, but then it ends at u of n minus 4. There we go. So at u of n is equal to 4, n is equal to 4. This turns into 1. This is always 1. That's 0, so that's a finite signal. So if we wanted to say how many elements are in here, we have 1, 2, 3, 4. So we have 4 elements. So n is just basically treated as our number of elements. So that's a quick little rule we have to establish. So now we have our finite signal. Now let's take a Z transform of it. So then is equal to, we're going to look at the entire signal, n is equal to positive infinity, n is equal to minus infinity of x of n, z to the minus n. There we go. And now you're saying, oh gosh, it's a sigma or a summation. And don't worry, we'll walk through the step just in case you don't know what's going on. So let's do the following. Grab a piece of paper. There we go. There we go. So let's just rewrite this as positive infinity, n is equal to minus infinity of alpha of n, u of n minus u of n minus 4 of z to the minus n. So how do we approach this? So that we know that if at n is equal to minus 1, that means u of n is going to equal to 0, and then u of n minus 4 is also going to equal to 0. So that means, well, nothing exists when n is equal to minus 1, any of the negative numbers. So that means we can change, we can do it following change. N is equal to 0 because that's the only point it exists at. But then if we look at the top terms, if n is equal to, 4, then that means, well, this becomes a 1. Is it 1? U of n minus 4 is also equal to 1. That cancels out that whole thing, so nothing exists at this point and all the further points that go up. So if we do this, let's do 3. But we can call this one n minus 1 for a surprise at the end. Alpha of n, d to the minus n. So now you're like, oh gosh, this is summation right here. What do we do? So the first thing you could do is, if you wanted to, you can just brute force solve for this system. So let's just look at n's equal to 0. That means alpha of 0, z to the 0, plus n's equal to 1, alpha z to the minus 1, and then plus, you see the pattern? And let's just do n minus 1. And we're doing it like this to show you a surprise. Alpha of n minus 1, z to the minus n minus 1, and there you go. Now you have the system. And you're like, okay, why didn't I just write the whole thing down? So what if n goes to like a big number? I can't do that. That's too big. So what we want to do is we want to find a little technique to make this simpler. So there's a little trick I wanted to show you. Well, it's not a trick. You see this pesky term right here? What if we wanted to multiply this whole thing by alpha and z to the minus 1 so that we can get rid of that and that? So we can do that if we were to do alpha z to the minus 1 of that whole thing, n minus 1, n is equal to 0 of alpha of n, z to the minus n is equal to, well, we get, this one is 1, alpha z to the minus 1 plus alpha 2 z to the minus 2 plus alpha of n z to the minus n minus 1. So there, no, n. There you go. So that gets rid of that n term. And then you're like, okay, and now what do we do? So there's a cool thing. What if we took this guy, this right here, and subtracted with that? So if we do the following, this n minus 1, if we took this alpha n z to the minus n of 1 minus alpha z to the minus 1, so we're taking this first term and then minusing this cool term, which is going to equal, well, let's just do that mathematics to show you guys what's going on. So we're looking at this term right here. If we do 1 times this, we're going to get, well, 1 plus alpha z to the minus 1 plus alpha 2 z to the minus 2 plus alpha n minus 1 z to the minus n minus 1 plus now we're going to do this term, so we're going to multiply this to this, which we already did. It's this right here. So minus alpha of z to the minus 1 minus alpha 2 z to the minus 2 plus alpha n minus 1 z to the minus n minus 1 minus alpha of n z to the minus n. Then you're like, oh, I see a pattern. Suppose we did this. See how this term right here, this term here looks similar? Can just cancel that all the way until we're left with this term right here and this term right here. And we're doing this because there's probably someone saying, I don't know how to do these systems at all. Yeah, don't worry, we're here to show you that. So if we wanted to put the final result, let's do 1 minus alpha z to the minus 1 n minus 1 n is equal to 0 of alpha of n z to the minus n of 1 minus alpha of n z to the minus n. There you go. But we want this. What we want is this. We want this. Ah, we can find that right now. 0 alpha of n is what we wanted to find initially, which is equal to 1 minus alpha of n z to the minus n 1 minus alpha z to the minus n to minus 1. And there you go. This right here is for finite signals. Now suppose that n goes to, the number of elements that we have goes to infinity. There's a whole bunch. There's an assumption. There you go. The assumption is that alpha should be less than or equal to 1. Actually, the magnitude has to be equal to that. Because if we look at this term, if alpha is equal to 2, then we have 2 times 2, 4, 8. It goes to infinity. This term goes to infinity, blows up. And we don't want that. And this term actually dominates more than this, so yeah, it goes to infinity. So if this were 0.1, then it's just 0.1, 0.01. It gets smaller as we go higher in n. So this actually disappears. So the assumption is alpha has to be less than or equal to 1, the magnitude. So if we took that into consideration for all general signals, then n is equal to infinity, n is equal to 0. Note, it has to be 0 right here. You can do shifting properties if you need to. Of alpha of n, z to the minus n, is equal to 1 minus alpha z to the minus 1. And there we go. This is the z transform. Z transform of x of n. There we go. So now you're like saying, okay, if we were to go back to our thing, what if alpha is equal to 1? What if alpha is equal to 1? So if we were to go to the time domain, the n domain, then we see that if we just plot these points, if we have a constant magnitude of 1 and it goes to n is equal to infinity, what's that? It's a unit step. So that means unit step. So that means if we wanted to do alpha is equal to 1, that means we're actually doing the z transform of the unit step, which is equal to 1 minus z to the minus 1. So that's a little thing I wanted to show you there. Hopefully that clicked into your brains. And let's do the following 3. There we go. Now we want to say, okay, what do we do? The next thing I got to show you is a z diagram, z plane, the z domain. There we go. So let's bring back our system. 1 minus z to the minus 1. I want to ask you this. Where does the system, well, where's the poles and the zeros? And you're probably saying, oh, we can see the pole. But I'll tell you now, there's actually one thing you got to do, and I will be checking for this on your assignments. You actually have a 0 in here. And you're like saying, what? How? If we multiply this by z, you notice that. And I think this actually is easier to see. So if you wanted to see where the actual zeros are, that's where it pops up. So the z transform of this system is, well, where do we have a 0? The 0, just like in the S domain in Laplace. Oh. Well, just like in Laplace S domain, we can plot the real and the imaginary. Z is actually going to have some real component plus some imaginary. So if we were to look at this system right here, well, z is going to equal to 0. At the 0 is going to be 0, so that's really easy to plot. There we go. And then the pole, we notice that if, well, z is equal to 1, that's a pole. There you go. So one last thing I got to show you is the unit circle. And that's how you would draw your little diagrams. And now you're saying, well, now we have this system. Now what else can we do with it? The next thing I got to show you is the residue theorem. And the residue theorem, just like in the Laplace transform, is what's the transfer, or if I were to say, well, in reality, instead of z to the n, we're actually looking at x of z. So the z transform of x of n results in this. So if I wanted to look at this system, what's x of z when z is equal to 0? It's 0. The magnitude is 0. It's just 0. But what if we're at the pole? What do we do if we go back into the time domain, the n domain? What does that result with? So if we look at this pole, we got to look at, well, what does a residue? What's the residue of that pole? So one thing I wanted to show was, well, with the unit step, suppose we had a constant c and 1 minus alpha to the minus z to the minus 1. If alpha is equal to 1, that's our unit step. But if we have this pesky c, the inverse z transform is going to equal to let's just call it x of n is equal to c, because that's a constant. The pole, what's the pole value? Pole to the nth power, and that's it. But if for causality, we want to add that right there. So the rule is, if we look at every pole, we can just do, whatever value the residue is, times the pole to the nth power, and then times u of n to make it causal. So that's the theory, plus C2 of pole 2, depending on how many poles you have. So that's what we wanted to do. So to demonstrate to you this, let's show you another quick example. This right here is 4. And we'll start with, let's just build a system. Let's just choose a random system. And the system I want to do is, well, just pick a pole right here. And it's on the unit circle. Okay. And let's just choose this as omega. So the thing with poles being on the imaginary part of the Z transform is you have to have a complex conjugate at the same minus frequency, minus omega. So where this is, well, if we wanted to mark that pole, 1 minus, well, the pole value, z to the minus 1, plus 1 minus p2, z to the minus 2. This is pole 1, pole 2. And if we multiply this, actually, like, this is equal to, let's just call it h of z. So if you wanted to take this into the inverse transform, it's really easy. It's not that bad. You just add these terms and you're done. So if you wanted to go, actually, let's just show that right here. P, actually, let's do re1, re2, re1, p1, plus re2, p2. All this to the unit step. Don't forget the unit step. If you don't put the unit step, you will get marked a point off. Oh, not for me, the exam. Just giving you a quick hint. Because we want to have stable systems, causal and stable systems. Okay, if you want me to give you a quick note on that. You recall that I just said, oh, what if alpha, like, alpha has to be less than or equal to 1. What if alpha is equal to 2, let's say? So that means the pole 1 over 1 minus 2 z to the minus 1. If we wanted to turn this into the real domain, h of n is equal to 2 to the n, 2 to the n u of n. You notice that if n goes to infinity, then h of n goes to infinity. That's unstable. It just blows up. So we want to look at the region of convergence. And that is, well, the first thing is all the poles have to be inside the unit circle. And we have to look at the farthest pole, from the center. So everything outside that far pole. So if we wanted to look at this system, then the region of convergence is this whole system. And then the region that converges here, you can do this if you wanted to. Oh, you got a big donut there. ROC. However, it's not stable. So this is a causal but not stable system. So it's not going to work. If we were to look at this example right here, actually, let's look at this system right here. If I had a pole here and a pole here, here's the unit circle. You note that it's a stable system. All the poles are inside. However, now we got to choose, our region of convergence. For it to be stable, we have to choose this so that we can have a stable system and a causal system too. We don't want any poles in our region of convergence. That's not good. So that's a quick note I wanted to make there. So now you're saying, well, what do we do? Prove it to me, David. So h of z is equal to, well, I'm going to multiply this. Well, let's just assume these terms are 1. 1 minus p of 1 z to the minus 1. And I will tell you this right now. This is 1. That means p of 1 is equal to e to the j omega. And p of 2 is equal to e to the minus j omega. So that's the pole locations. 1 minus p2 z to the minus 1. There we go. If we want to multiply the bottom term, so let's do this. 1 minus e to the minus j omega minus e to the positive j omega. Oh, z to the minus 1, z to the minus 1, 1. Plus, if you multiply this and this, you get 1, z to the minus 2. So that's that bottom denominator. But there's a rule, and you see that right here. If we multiply, let's recall cosine of omega is equal to e to the j omega plus e to the minus j omega divided by 2. So if we multiplied, well, e to the let's do this, to the j omega plus e to the minus j omega by 2. So we have this, and if we wanted to multiply this, then the resultant is minus 2 cosine omega, z to the minus 1. So that means this whole term right here turns into 1 minus 2 cosine omega naught z to the minus 1 plus z to the minus 2. And now you're saying, okay, so we noticed that the pole is at the unit circle, but what if it's not on the unit circle? So there's a term. If we put a pesky r term in here, you know, r, so that means, oh, if r is equal to, well, half, 0.5, that means the pole is going to be here at the distance 0.5. So it's easier if you can see it here, r, 0.5, and this e to the j omega just spins it around the circle. So we just put an r here, r gets r squared, and yeah, we can just punch that r right there and r squared. So that's that little proof for how to get that nice resonating denominator. And now you're saying, well, how do we do a PZ map? And you probably notice a mistake, and that, well, this right here is not the real z-plane map that I want to draw. So this is not the answer. The answer is actually going to be something cool. So I will show you here. 5. And we are at the 23 mark. Go. So, and this is what you're going to do in your assignments and on the exam. If, let's just pull this one out, 1 minus 2r cosine z to the minus 1 plus r squared z to the minus 2. Where are the zeros and where are the poles? And if you're going to say, oh, there's only 2 poles, well, you're wrong. There's actually 2 zeros. And you're saying, oh, where's that? If we multiply top, z to the squared, to the minus to the squared, therefore we get z squared minus 2r cosine z to the 1 power plus r squared. Now you can easily draw the system. And that means you have 2 zeros here, and then you have a pole here and a pole here depending on your omega term. Really easy, right? So this is how you would draw your system. So if you go to an interview and they tell you, okay, draw me the poles and the zeros of a resonator, and you just give them the poles, they will just turn you down right on the spot, because this is a really practical, really trivial stuff. So on the assignment, I will be taking off a point if you don't put the zero. So just warning you. But no, it's because this is a practical thing. There's people in 722 who are like mixed signal design who just don't really see the zeros. I'm like, there's a zero in the thing. It doesn't affect your magnitude, but it affects your phase. So don't get it wrong on the interviews. So now we're saying, okay, now what do we do? I want to show you an example on MATLAB. So if we go to MATLAB, and I already have some stuff done. I think this right here. Nope. This right here. Boom. I've already whipped up some cool stuff to show you, so we're gonna clear all stuff. We're gonna have a omega naught of pi over 3. This is what I chose. So we're gonna expect to see the poles at an angle at pi over 3. The radius is 1. The pole location's here at positive j omega. The other one's at minus j omega. And then to get the z terms, the pole locations, we gotta do 1 minus pole p1. So don't forget this minus term, because that's the rule of the Laplace, the z transform, sorry. And then the same thing with this guy. To get the denominator, we just convolve them. And then note, we're just doing a really simple resonator, so we're just gonna put a term of 1 there. So if we wanted to draw the z plane, so let's look at that. Boom, does that look right? Look at that. That thing right there is at pi over 3. And if you don't believe me, let's just do pi over 4. You understand what's going on? See? As if you create an angle from here to here, you see that, pi over 4 or pi over 2, wherever you want. That's how it works. And then you're saying, okay, David, now tell me what that r value does. And that's the reason why I edited your assignment, so that you understand what's going on. Hopefully it clicks onto your brains and you're like, oh, now I can do systems. So let's just change it to 0.5, because that's the easiest one to see. And you're like, oh, but you're like, I can't see if it's 0.5, man. All right, then let's just choose a really small angle. And the small angle we could choose is like 100. And you're like, there it is, you see? So that's why we do these systems. Is it making sense, everyone? Hopefully it is. And now you're saying, well, what do we do now? What's the magnitude response, or what do we get from these systems? So I'm going to try to show you guys what's going on. So we're going to try and figure out the magnitude response. So for engineers, we like to look at the actual unit, the unit circle. And this is actually leading to the Fourier transform of the system. This is what we want. It's a spectrum. It's the Bode plots. It's what you always see in your circuits classes. So we want to analyze the system at every point and just look at the value. So I whipped up a little thing right here. And let's pull it up right here. HDen. And there we go. And HZ. And there we go. So this right here is 1 divided by, well, whatever resonating terms I had there. Here's radius, z to the minus 1. You can also do z squared. You can do that, but however, I'm going to show you the governing equation. This right here is your governing equation that you need to know. As long as you do this, then you're fine. I saw someone like, oh, they put the real part, like alpha and betas in their things, and like they separated the imaginaries and the real parts. You can do that, but that's a lot of work. Don't do that. MATLAB does a lot of stuff for you, so you can literally leave your terms like this, and MATLAB will take care of that for you. So just like what we did on the previous stuff that we've done, if we wanted to map this on a unit circle. So we're gonna just look at -2 to 2, -2 to 2. Mesh grid it. It's the same stuff, and we're gonna analyze this system. And let's look at the this right here. There we go. So we're just gonna look at what the system does. Boom. And you're like, whoa, David. And you can clearly see that we have 2 poles, and a 0 that dominates. It's a huge 0 because there's 2 zeros there. And you're like, so that's making sense. But you're like, I can't see that, David. And I'm gonna say, yeah, I don't blame you. So what I did, I whipped up something pretty cool. You can do this if you want, but you don't have to. Recommend not. Let's do this. There we go. No, that doesn't actually do anything. Should have plotted that other point. Let's just plot this guy right here. I'll show you something cooler. So the other thing I wanted to show you is, okay, what if we wanted to do a magnitude response of this system? So we wanted to look at h of I think j omega. So we're looking at when the real part of z is equal to 0, or not 0. It's gonna be on the unit circle. It's just gonna equal, well, 1. No. Sorry. If z is equal to re to the j something omega, then we're just gonna look at when r is equal to 1. So we're just gonna look just at that unit circle. So j omega, e to the j omega. There we go. That's what I forgot. E to the j omega. That means we replace all these z to the minus 1s with j omegas. And now we're just literally looking at the unit circle. And we're plotting that. And you're saying, okay, how do we do that? So one thing I'm going to show you is if we were to look at, well, you know, the h e to the j omega at pi over 3, if we were to look at this like, oh yeah, we're going to have some signal. Oh gosh, you're probably going to see something like this. And then consequently on the other side, minus pi over 3, you're going to be like, oh, and then, oh, you're going to probably see something like that. And then there's another rule I want to tell you. 2 pi. And this is in advanced like DSP classes, so 480 will tell you about this, is that the spectrum repeats for discrete systems. So if we were to go into here, we'll probably see another peak like, oh, yep, oh, and boom. So you'll probably see this in your diagram. So what I want to show you is the following. If we were to go to here, so we're using the Frex Z, run that, untitled, oh, that's because I forgot W. Boom. Oh, that's where it came from. So what I wanted to show you was I drew this black circle right there to show you that that's a unit circle. But you see that magenta thing right there? Well, that's supposed to represent, well, the magnitude response itself. So I actually put a DC gain in there. Let me see if I can take that off. Ah, there it is, DC gain. You see that pink line? That's exactly what you'll see. And I will show you another plot too. Figure 101. Plot. H, F. No. Freaks. HF power. Yep. Plot HF power. Nope. There we go. Omega. There we go. So that's what our system is actually looking like for this guy right here. Actually, yeah, it looks right. Hold up. Looks right, I think. HF power. Log of this. Yep. Not that bad. Okay. But the point is, now you understand what's going on with these systems. It's basically, well, if we were to look at the frequency response should look like, well, if we were to squish this if I wanted to, if I grab this guy right here, I can see that, but why does it not look like that? It's okay. Don't worry. Let's clear all. Let's do pi over 4. I have a great idea. What if we just make our system actually unstable? 0.9. There we go. Oh, there we go. Now we have distinct peaks. There we go. Actually, yeah, you can see that better. See, you see how, oh, you got these little peaks right there? That's exactly what we're going to see. So here's actually at the frequency where the frequency is, well, 0 or DC. You can see these peaks. Ah, I see. Kind of looks like the Batman symbol. So that's what I wanted to show you. So if this looks like this, then you're doing it right. So what else do we got to go over? Yeah, all this is basically the same. Can you understand these systems? Z-plane, you know exactly what's going on. The residues, you know how to get that using the residue theorem. I've already showed you via hand calcs. And because it's a resonator, you will see it resonate. So basically the same thing. So you already know the residue times the pole location to the nth power. You have to use the residue theorem. So actually, let's just show you the residue of this guy. I will show you that right here. Yeah, I'll just show you right here. R, P, K. Actually, let's not do that. R, Z, P, Z, K, Z. Residues of Z. Of Z, num, Z, then. There we go. We see that, well, we get this term right here and this term right here. So if we were to put that into, well, our numbers, well, if we plot this number and we plot this number, here's our residue, and then we put this to the power of that, then we should get that. There we go. But I'll tell you right now, the pole locations, I'll show you on a piece of paper. There we go. If you get this situation, if you get, I don't know, some constant c divided by 1 minus e to the j omega, yeah, I think we can do that, z to the minus 1, then your residue of that is going to be, well, whatever value c you get there, e to the, well, sorry, j omega n. There you go. And that's in the H domain, the N domain. So that's basically how you would solve for that one. But you will have another term that pops up. You'll have the complex conjugate. And that actually cancels out the imaginary values to hopefully help you solve that system. So that's how you would do that. Yeah, I'm just showing you a couple things. There you go. And then the same thing with the step function. So generate y of z when x of n is equal to u of n. So you already know what the unit step is, so I'll show you that right here. I'll show you on a piece of paper. If you took your system, 1 of 1 minus 2r cosine to minus 1 plus r squared z to the minus 2, and you multiply this by, well, 1 minus e to the minus 1, because this is right here is the unit step in the z domain. If you convolve this with this, then you get your new denominator. And then you can do the same thing, the same process, you know. Let's go back to the assignment. Use the residue stuff. Using the residue function, now you can get your points. And then you should notice it should settle to a value. You should see a value, a gain value. So hopefully that can help you around. So the next thing I want to show you is this part right here. I'm just breezing through all this stuff to hopefully make sure you guys understand what's going on. So draw and label a direct form 2 block. So let's do this. Hopefully this video is not too long. I'm trying to make sure it's not too long because the last one took like a long time to publish. And I'll just show you a really quick example. Make sure everyone's doing their own work. 7. There we go. So if I had some system y of n minus, I don't know, alpha of y of n minus 1 is equal to x of n minus beta minus 1. that if we were taking this to the Z transform, the rule is, well, you just look at the delays. If there's a delay, you put a Z. So this right here, y of n, the Z transform is going to be y of z minus alpha. Well, if you take this to the Z transform, you actually notice that this actually comes up with a value of z to the minus 1 y of z minus a condition of n is equal to minus 1. I think that's it. Yep. So we're looking at a previous value, but this is for saving your states, or what's your previous state. Is there any numbers in your system? X of z minus b. And the same thing applies with the zx terms, minus x of minus 1. But for now, we're going to assume that y of n is equal to minus 1 is equal to 0. So we're going to assume that it's a clean system. We don't need to worry about this system right here. We don't need to worry about this. So if we were to just factor out all the z's or the y's, we get y of z. Get 1 minus alpha. And x of z, 1 minus beta. Z to the minus 1. Then if we were to divide this by x of z, and divide this by 1 minus alpha to the z minus 1, then h of z is going to equal 1 minus beta z to the minus 1, 1 minus alpha z to the minus 1. If we wanted to draw a quick block diagram, really quick block diagram, this is the transfer function of that. But if you wanted to get a quick block diagram, we can do x of n minus beta x of n minus 1 plus alpha y of n minus 1. We notice that we have one delay block. If we were to do a a direct form 2 block, we have our input directly going into our output. And we have two delays, or not one delay. We have a positive alpha and we have a negative beta. So for your assignment, you'll notice that, well, for the state space systems, here's a hint. I will give it to you. Q of n plus 1 into a z to the minus 1 block. A delay is that. It's going to turn into Q of 1 of n. For your next state space systems or state space equations, well, you're going to solve for the next state. So Q of 1 of n plus 1 is equal to the input, don't forget that, plus alpha of Q of 1. And then you're going to look at your output. Y of n is equal to, well, whatever state's here minus whatever is that there. So just to save on time, because this is right there, I'm going to look at, usually this one's a positive term, but it's okay. Minus b plus alpha Q of 1 plus x of n. If you wanted to do your block diagrams, you notice that, well, a is going to be this little vector. But the whole point is, this is the stuff you will have to do for a second order differential or difference equation. You'll notice that you have to set this term to Q of 2 of n plus 1 and do that same process. How to check if your work's correct? Well, you can go to MATLAB and let's see if I can show you this right here. Let's show you this. Actually, let's just brutally show you what's going on. Here we go. A couple things I need to show you. There you go. So this right here is probably what you're going to be seeing on your assignment. You'll see that, oh, here's this, and here's your numerator, and it looks similar to your assignment. Here's your denominator, and then you're going to do EQTF length of that system. So you know what I'm going to do? I will do the following. Oh yeah. Let's clear all. Get rid of that residue. And there you go. So this is what you're going to be seeing. And note your hand calcs will be matching this. But you got to prove that to yourself. So can you do this? Are you able to do this? If you're not getting these numbers, then you mess up somewhere. So make sure you're able to do that. And I'll get to one more point, because this is going to be on the exam. And you already know the proof to it. It's in the Laplace domain. I'll show you right here. So you're going to see something where you're going to have q of 1, n plus 1, q of 2, n plus 1. This is kind of your solution. It's going to equal to some alpha of q of 1 of n, q of 2 of n, plus beta x of n, and then y of n is equal to c of some, not c, that's c of q of 1, q of 2, plus d of x of n. This is a 2 by 2. So if you were to do this system, you note that if you were to go into the z domain, q of 1 of n plus 1, z domain is going to have z to the minus 1, q. Let's call it q. Yeah, let's just do that, q of 1. So let's just call this one q dot, or q of n plus 1 x. And so basically what I'm trying to say is this whole thing, this whole q is going to turn into this. So you can prove the same theory, and I think you'll get eventually to an equation where it's going to be y of z is going to equal, I think, let me just check what I have here just to help you. And you probably will see this on the exam. So you'll see the following. C of z I minus a minus 1 b plus d x of z. So try to prove this on your own. And you've already seen it. It's in the Laplace domain. It's the same thing. But if you can do from here to here, you know, you got your alphas, your betas. Make sure you do that. Make sure you show your alphas and your betas. Can you do it? Oh, I just used the transfer function. No, don't use the transfer function. Don't use TF to SS. Don't do that. Or you will do that for showing your work, like proving your work. But the whole point is, can you do it by hand? If you can do it by hand and you can do this, and then you can find h of n, this right here will give you your residues. Can you find the residues by partial fraction expansion? You're done. That's the final, well, kind of the final, it's your next exam. So if you're able to do this on your own to a point where, like, oh, you know your alphas, you know your i's, c's, b's, and d's, then you can solve for anything you want. So right here, let me show you this. So that's your system right there. And now you're saying, okay, David, now we have a system. Well, now you know that this is the answer you're looking for. You better know how to do this, and you better know how to get the actual transfer function from these coefficients. Can you do it? If you can't do this, then yeah, you're not gonna have a fun time on your exam. So make sure, try to do this on your own. A, B, C, D. If you can find h of n from these coefficients, from these numbers, from this equation, then you're set. You're golden for this class. And let's try to do a little bit of your assignment. Oh, I should probably show you what this does. So this basically does F9? Well, it just turns it into some coefficients. If this were z squared, z minus z1, z0, it basically just shows you the poles. Don't worry, this is not that bad. You can use this to prove that, oh, you've done a good job. But yeah, don't worry. Actually, what it basically does is like, oh, it just doesn't assume it's like this. So it takes this and takes it to this, and then it's easy to put it in the ABCD domain. So that's that. Oh, that's a different assignment. Let's try to do the next part. This is all the same. I think I need to show you one thing, but I don't know if it's gonna be a problem. Let me see. Here we go. Rocking system. So there's one thing I gotta show you, and this is something you have to be aware of. If you're trying to find your system, like, okay, my let's actually just copy it from here. So if you were gonna take some system and you're like, okay, now let's turn it into a system using the state space equation, like the state space function ABCD. If you were to not put this right there, that turns it into an analog system, and then your system's like, oh gosh, it doesn't work. To turn it into the discrete domain, to turn on the discrete mode, you put this -1 there. So that's how you would approach that. And I think after doing that, everything's the same. How to show your work for this one? Well, you'll see that a DC gain pops up. So let me show you one thing. I'm gonna try and wrap everything up in one big video. And we can start with I don't know, let's just do h of z is equal to what do I want to do? 1 minus z to the -1, 1 minus 2 z to the -1, z minus 2. So on the unit circle, you've probably heard me say DC. What's DC or frequency? The unit circle is something we can, like, change our frequency. So if we were at f is equal to, some point here, we can go to, like, our highest frequency here. So f increases as we spin around the circle. But if we go to this point right here, that's our DC value. So that means that's where z is equal to e to the j0, z is equal to 1. So all you gotta do is, well, you're gonna probably suppose this is a b term right there, and suppose b is equal to 0.2 or something like that. Then if you were to do, if z is equal to 1, then that means 1 minus b at z is equal to 1, 1 minus 2 minus 1, and then you get some DC gain. So that's basically what your system does. If you turn on your system, what's the response? What does it do at DC? So that's your DC gain. So that should hopefully get you going with what's going on. Are you understanding what's going on? No. It's okay. There we go. I'm trying to see if there's any trouble for this. And yeah, it's all the same assignment. If you understand the previous assignment, then this assignment should be really straightforward. The step function. That's really easy. The impulse, let me check. Yeah, it's all the same. It's all really not that bad. Do you understand what's going on with PZ map? This right here might be a little, well, it's not that confusing. If you understand what's going on, you're convolving or multiplying your unit step to your actual system. You already know how to do that from the previous assignment. All you do is, well, you look at the numerators, you know that well. Let me just show you one last thing. If you were to do the unit step of n is going to be, well, you already know this, 1 minus z to the -1, which is also equal to z minus 0, z minus 1. So if you put these in vectors, 1, 0, 1, minus 1, now you can solve for your system using, well, the transfer function. If you were to use, okay, let's just show you a little demonstration. Hopefully everyone knows how to do this. No, I don't know. It's okay, man. Actually, let me just show you. Actually, nah, screw it. Let's just show you right here. There we go. Oof, I'm almost at the hour. Okay. If we were to go into the Z domain, that's it. And now you can use your transfer function. Let me show you that. And you can multiply this. So don't forget that. And then actually you can't multiply this directly. You need to turn this into the state space representations. Turn this into a state space, you know, well, using the SS function. Just punch in this system into SS and then you're done. Multiply whatever system you created with whatever this system is. And then just do the impulse and you're done. So really simple assignment. This is as much as I can show you, and hopefully yeah, this should be a really easy assignment. Number 1 should be just like, yeah, the first half is all just breeze. The only problem you might have is probably example 9, but it's not that bad, honestly. Just draw your system. You already know how to check your answers. That's with this. So make sure you get it right. I will be checking. The credit goes to number 9 and number 1. If you can do those, then yeah, you're set for an exam. And yeah, that's basically it. So I don't know if I'll be making other videos after this. I think this is probably going to be the last one. Wanted to show you some other cool stuff, such as well, I can show you one last thing. This is probably if you want to go into systems design. And you're probably saying, well, okay, David, so what do I want to do? So suppose I had some, you know, some signal right here, like, you know, it's a cosine signal, cosine function, cosine of, let's just say omega naught. And it's just, you know, spinning in a circle. Actually, omega naught of t of s, I think is what I'm going to call it. So if we wanted to take this and transform it into the Z transform, you're going to notice that, well, it's going to have some resonating frequency. It's going to start resonating frequency. However, the complex conjugate, it's going to have some type of phase, but that's as much as I can show you. Actually, what I really wanted to show you was the Fourier transform. That's the whole point of what I wanted to get to you. The Fourier transform of your system. This is where all the crazy engineers go crazy. If you wanted to do cosine of omega naught t, okay, I'll call it actually 2 pi f t because that's how I'm used to. If you go on the frequency domain, you can post this as, you know, that, a point right there. But if you were to put this f right here onto the Z transform, that right there is there. If you were to draw the double spectrum, because the Fourier transform also has negative frequencies, you notice that you have a spot that comes right there. So this is the powerful thing I wanted to show you. And that's the Fourier transform, and that's introductions to EE360 one, where you're going to analyze, systems, signals like this, periodic systems. That's a keyword. Signals can be used in the Fourier domain. So that's probably where I want to leave off. And actually, if you wanted to, if you had like a whole bunch of signals, if you had like some random signal that looked like this, then that can be described by, well, like in the T domain, you can describe that by it probably has like some noise there. And if you added all these signals up, you can actually get this. So that's the powerful, beautiful part of these for the Fourier transform. But that's out of the scope of this class, but that's the introduction to EE360 one. So that's it for all. I think that's it, and it's been a pleasure trying to show you what's going on with how to use MATLAB, and hopefully everyone's had a good time. You know what's going on. If I show you, if you go into industry and you see a plot like this and you're like, oh, you know exactly what's going on. You see a magnitude response like this, you're like, oh, you exactly know what's going on. So hopefully you understand what's going on. And yeah, that's about it. Well, let's finish my song. Oh yeah. Wait, I wanted to show you the drop. Oh, by the way, this right here is a Fourier transform if you wanted to see that. Bass signals. This right here is that system right there. That's the thing that's cool about signals and systems. Alright, take care everyone.